So this is GPU accelerated security. So first off, standard, who am I? I'm Andrew. It's my website if you're interested, Twitter, GitHub, some notable projects, and I'm a fourth. So before we begin, I felt it was worth putting up a bit of disclaimer. My knowledge is absolutely not absolute. There are very likely things I've missed. My research primarily focused on intrusion detection systems, or is focusing on intrusion detection systems. I've just recognised similarities in other areas that it could be applied to. There's loads of things that I would like to explore, but I simply do not have time for. It's 53 days left. Sorry to all the fourth years sitting in the room. And if I've explained anything poorly or general questions, please just leave them to the end because I've got way too many slides to cover for the time slot. Another thing is it took me hours to fully comprehend some of the topics I'm going to go through, so I'm going to try and explain them the best I can, but don't worry if at the end you're completely confused. So the other thing is I can remember being a first year and completely glazing over some talks because there was just key terms or acronyms not used, or that I didn't know. So there's some of the things I might say throughout this talk, and if you don't know what they are, have a quick look. Most sort of notably is the HEPFAC algorithm, and when I say kernel, I don't mean Linux kernel, I mean a function executed on the GPU. So I want to sort of start this off with a preface. Lots of applications try and implement GPU support, or there's initially we will do GPU, but as you can see, especially in the case of Securi-Tay, things don't always go to plan. There's often, at least from the open source projects I've been able to come across, a bit of an issue with regards to continuing support for GPU. And then out with open source, a lot of things just, here's a paper on this awesome concept and paywall. Or there's no source code or anything, even proof of concept provided to back up the claims they're making. So, bit of a, before we continue, notes. GPUs aren't necessarily a complete replacement for a lot of these tasks. A lot of the things you're better off having a balance, a blend of CPU and GPU. And for my particular examples, an intrusion detection system does a lot more than just signature matching. That's just the area I focused on because I'm time limited, basically. So first off, my methodology and my direction. Started off with when should I actually be using a GPU. Effectively, you need to do a computation on a huge number of items. Computation doesn't rely on the computation of other items, so it's fairly independent. And it's fairly simple. There's a bit of star in there. Basically, as long as you've not got too many branching operations, you'll be fine. But if you've got lots of branching operations, the processing of a GPU, the cores are fairly stupid. So they're not as fast as a CPU would get from them. I'm going to skip this bottom half because it's basically the inverse of the top, and I've got quite a lot to get through. So to summarize, what's the GPU good for? Performing simple operations on a huge volume of data. What's the caveat using the GPU? The data must be copied to the GPU, and when you want to get your results back off the GPU, you need to copy it all back off again. And that introduces an overhead. So my methodology for how to go about approaching this to speed things up was to maximize, minimize, and then just generally optimize. Again, I'm going to apply these principles somewhat to like file carving and intrusion detection systems. So first off, maximizing. So when you copy data to the GPU, there's overhead, as if you were compared to if you were just to execute that same function on the CPU. So the more often you have to copy data, the more often you're going to encounter that overhead. It's fairly simple stuff. But by maximizing the amount of data that you copy at once, you minimize the number of copies that you have to make, so you encounter that overhead less. So my solution to this was buffered copies. Effectively, as long as the data isn't time sensitive, basically hold it back a bit and then try and send over as much at once. With time sensitive data, you would just have a timeout. But you would actually have that with all data because you wouldn't just be like, I'm going to wait until I get another packet so I can finish off this buffer, and you could just be waiting indefinitely. It depends. So how have I implemented this? I have a mock-up intrusion detection system, nowhere near advanced as like Snort or Surcat or anything you get. It was more just to prove the things that I've run through. So I basically, every time I capture packets, I'm loading them into a buffer, and I'm copying that buffer over once it's reached a sufficient size or a certain timeout period has been reached. So, second part, there's sort of two parts to this. They're kind of similar. This is minimizing. So, similarly as to maximizing, when the copies introduce overhead, the more data that needs to be copied, the longer it takes. Or I should maybe say the more bytes that it takes to represent that data, the longer it takes. So if you can represent the same information in less bytes, it's usually going to be faster. So my solution for that one was what I've called bit indexing. There's probably another term for it. It's a simple enough idea. It's probably been done before. I just could not find anything on it, so I've just gone with that. The other one is basically minimizing the members. So if you're copying over objects and you've got lots of unnecessary members, you're just wasting time. If you don't use those except for debugging, do not put them in the final version. Okay, so these are some more like just general summary of optimizations. So there's texture memory, shared memory, and global memory. They were on that first slide of here. Some terms I might cover. In case you didn't catch that, though, texture memory is effectively a cache for texture data. 64 kilobytes, it's fairly small. If you can fit your data in that, you've got complete control over that cache. And so that can lead to some massive performance improvements in your application, especially in the area of string searching where you might have thousands of patterns to search through. Shared memory is kind of similar, except it is the level 1 cache of the GPU. And effectively, you fence off a section of it and you say, hey, that 32 kilobytes, that's mine. You don't get to dictate that. I get to dictate that. And then there's global, which is just like the GPU equivalent of RAM. Still fairly fast, but not as fast as the other two methods. Buffering, CUDA-MEM copies, covered that. Minimizing, maximizing data. One that's often missed out, at least from the research that I've done, is using multiple GPUs if they're available. Certainly in the CUDA standard, it's really, really easy to make use of multiple GPUs. Loads of applications just fail to do that. Async, all the things. Asynchronous tasks have existed for quite a while now. The support for it's pretty good. It's often not used. Use your threads. So although you'll be doing a lot on the GPU, it doesn't mean you can just go, oh, single-threaded task, I will literally run everything on one thread. I've seen that in a lot of applications as well. And if you can work out how, I've not been able to so far, single launch kernels seem like a really great idea. The idea is effectively that you launch the function once and you just keep copying data to it instead of relaunching the function with new data. So you're minimizing that little kernel launch overhead. There's another one as well that I only just remembered like 2 minutes before this talk, which is memory padding. So if you've got the space to allow it, you should pad your data so that it basically aligns in memory chunks. So when you fetch that, you're not having to get another chunk with it and then get another chunk. You can try and make it so it's just one request rather than 3 or more. So applying what I know. So I felt that it's better to start off with a quick representation of what AHO Corsic is, because although it's fairly common in multi-string matching, it's not one I'd encountered before starting this, so I figured there might be other people who hadn't encountered it. Not really going to talk through this too much because I think the visualization speaks for itself, but I'll just get through it. So we start off with our patterns and we effectively build a tree out of them. And I'm just basically going to click through this and kind of see what it's doing. I'll just note that at this point I gave up because I was doing this on my laptop with a touchpad and it was just a pain in the arse to build this diagram, etc. And then when you're searching for a pattern, it just works like that. So that's how you would represent it, a CPU with nodes and pointers and all those lovely luxuries. On the GPU, you've not really got the luxury of all that. Particularly in my case, all that is in a single dimensional array, and I've got to represent that somehow. So enter the HECFAC algorithm. It's based on Apple Corsic. It's just an extension that effectively compresses some things. So same principles, root node, end nodes. Patterns are stored alphabetically. The key part here, which will help on the next slide, is the nodes are made up of an integer offset, which is the location of the first child of that node, and an 8-length array of 32-bit bitmaps. And those bitmaps collectively represent all of the ASCII letters. You'll see why that matters again on the next slide. There's population count fun, which allows you to basically count the number of children, find the location of a child, and also check whether a node exists, or whether a child exists in a given node. So this is what that looks like. I've tried, again, to explain this as best as I can, but this one took me quite a long time to get right. So for the example of pattern ACD, or ACDDD, you would start off with your root node 0. You look for the population count up to A. A is the first one in that, so the population count up to A is 0. And then you add the offset, which is the location of the first child, and that takes you down to node 1. You basically can repeat this process, and I've got the calculations down the sides, because I felt that the arrows themselves wouldn't justify or explain well entirely what was going on. But you can effectively repeat that same process to work your way down through the tree. It's worth noting that this implementation of it is the implementation where you're only looking for the index of that pattern, not specifically what pattern it is. If you want to know what the pattern was, instead of having one final node, you would have a final node for each branch of the tree, and instead of it just being there was a match, that final node would basically represent what the pattern was. So previous slides, you might notice that there's DEF and there's also another DEF right at the bottom. Those nodes can actually be merged. Merging is a bit more complicated than it looks. Looks fairly simple in this example, but it's pretty awful. I've got a 200-line function that's not pretty at all. The key points, though, is mergeable nodes share the same children. Merging is done in reverse order to maintain the alphabetical requirements. The alphabetical requirement is so that the population count method will work when finding the children. This one here is bit indexing. Again, there's probably another name for it. It's just I've not encountered it before. It effectively allows you to represent a single index in 1 bit rather than in 1 byte. So I've tried to give it a decent example. This string of data along the top, so random data, hello world, exclamation mark, wouldn't be broken up like this. It's just broken up so that you can visualize better what's going on. There's a little bit of bitwise magic going on in there. It's effectively saying which array would this be located in. So for that first one, it would be array 0. And then it's saying which bit should I set according to the index. And that one there is effectively just shifting the bit across by the index relative to that array. So the real index is 7, but the way that we interpret it would be like 7 on this slide. Hopefully that's an okay explanation, but again, this one took me a lot of playing about with to get right. So the one thing with this is if you use a byte to represent this bit index, you obviously get 8 bits in a byte. If you went for a short, you'd get 16, and if you went for an integer or any other 32-bit types, you get 32 bits. The nice thing about that, though, is you can actually check to see if you've got any matches in any of those 32 bits when you're getting your results back by just comparing it to 0. So if it's 0, you didn't get any matches because none of those bits are set. But if any of those bits are set, then it's not going to be 0. So implementation, experimentation, etc. Digital forensics, file carving, immensely data intensive. When you're searching for file headers, basically a chunk of data will be copied to the GPU. You would search that, and then a result array, typically of the same size, would be copied back. So if you're copying 2 gigs of data to the GPU for searching, you would be copying 2 gigs back. That'll take a bit of time. That's assuming as well. That's assuming as well that it's a single byte data structure that you're using to represent the results. If you were wanting to get the index, for example, of the results, and you were using an integer to do that, then that would be the same size to represent that. By comparison, if you were just getting the index, you could use a single byte, or a single integer, depending on what you're doing. And that would be good for, in the case of the byte, 8 locations. So in that example there, if you're offloading identification to CPU and using bit indexing, instead of a 2 gigabyte result array, about 0.25 gig result array. And alternatively, you could use that in addition for fast access. I thought I'd put up a bit of code, but it's pretty disgusting. So again, don't worry if you don't get it. But I wanted to point out that this code down the bottom is effectively doing the same as the one above, or has the same outcome, just that the one above can be significantly faster. So I ran some benchmarks last night because I didn't want to come here with this is faster, honest, just trust me. So this is time in microseconds. I did only test one tiny bit of data, but I was just bashing together some benchmarks to test with. So that's only 1 meg of data that I was testing it against. But I've got comparisons of bit indexing versus Boolean indexing for every single location as a match. 1 in 20 locations as a match, 1 in 50. And you can see for yourself the time differences. The only one that it didn't perform as well in is when all locations are a match, and that would just be the extra overhead because of the multiple if statements. So future work for that particular section, working out if there's another name for it. Again, there probably is. Testing on much larger data. Again, that was only 1 megabyte I was testing with. I would be scaling this up to hundreds of megs, possibly even gigabytes. Determine if it's faster to separate the indexing and identification. That's something I've not yet tested. I want to get into that. Testing more and fewer bytes for the storage method. So that particular method I was using was a integer. So it was testing 32 locations at once. It would be interesting to test a 64-bit data structure to see if it sped up, or if that would cause additional slowdowns because of the more results to check through. And then I think it'd be faster than running 2 searches because assuming you were able to copy over more data to the GPU on that initial search because of the space saved with the result array. But again, I need to test that. So purely theory at the moment. So a bit about specifically what I'm doing. My dissertation is focused on network intrusion detection system optimization. But I want to make something more sort of general because, as I said, this problem applies to a lot of things. So I'm actually developing a HEPFAC library. So it's an implementation of the algorithms that I've just discussed. Sort of general purpose, easy to use. I'm just going to say it's fully prototype. There's probably things in it that could be done better, but I like to think that the concepts are there that can be built upon. HEPFAC algorithm, it's not mine. It's described in that paper there. So if you're interested in the algorithm itself, check that out. The only bit I've added to it is the bit indexing and the other optimization methods. So I also wanted to show some benchmark data from the string searching algorithm that I was using. This is extremely old, extremely unoptimized. This was my feasibility demo last year. I've not done anything on that one since, because I've been working on other areas, but all my final results will go up on the website once they're done, as well as all the research that most of this talk is based on is already on the website. So some important things to note is it's pretty fast, but it's not as fast as it could be because there's no texture memory in use. There's no branch minimization. This was bad. Lots and lots and lots of excessive copying, needless members in each node. I had so many debug members. I was like, I just need results. But again, I just wanted to show that I'm not just speaking entirely theory, and I have actually done some things. Point of note, the time there includes the memory copy time, whereas a lot of results just glaze over that entirely and go, yeah, the processing time's fast. We've got 27 gigabytes per second. We're going to completely ignore the fact that we needed to copy all that data to the GPU to actually do it. So I think it's better to represent the results in a realistic fashion. Like, that's it with the memory copy time. So this is my final design for now. I've got the bit indexing for the return type, packet identification offloaded to CPU separately. Again, I need to test whether that's actually faster. I've got my buffer system for copying the packets to the GPU. I'm using HEPVAC algorithm to build my tree for failure states, which is copied to texture memory, which is then compared. That's pretty much it at the moment, but there could be more added. Any questions?
So you've got this, which is essentially a clever search algorithm, right? And knowing enterprise programmers who design things like network intrusion detection systems, they're not really going to want to use that because they're going to want to use an equal sign in their code rather than that. How much of that could be hidden from general programmers in a library or something like that?
That way, yeah. So if I go back through that, the contrast in that's really bad. If I'd known it was going to be slightly better, or that bad, I would have done it with light theme. But I've effectively got it down to, this is the source that you want. This is what you want to search against. Go. It's fully... I've made it so that the default implementation for onResultFound is not implemented. You have to override that. So it could... I'm trying to make it so it would be easy enough for anyone just to pick up and go, okay, onResultFound, we want to do this. But again, I'm a student, not developer, so I'm kind of just guessing as to what I should do rather than knowing exactly what I should do. So I'm trying to build an interface that's easy to use, but again, it is just guesswork for me at the moment.
Okay, thank you.
So your actual intrusion detection system that you're using is currently just doing signal for that.
Yeah.
Are you thinking about maybe in the future expanding your intrusion detection system?
So really what I would, if I had the time, I would have really liked to have integrated this into Snort or Securi-Tay. The Securi-Tay CUDA code was just too broken for me to touch. And I found Snort really hard to read, just because of the sheer scale of it. I think if I was doing this as a thesis, absolutely, I would have no problem implementing it, I like to think. But with being an honours project, I just didn't have the time to do with such a wide scope. There's actually even things on that I've had to just cut out. I originally had DPDK, libpcap, and pfring as like all as collection methods for it, but there just simply was not time to implement all of those. So that is the collection method for that is just libpcap. Yeah. Else? Okay.